Class 11th, Subject Physics, 8th chapter, Sound. From this chapter, let us see factors affecting velocity of sound in air. Factors affecting velocity of sound in air. So in this point, we will have to study different factors which will affect the velocity of sound in air, and therefore in this point we will have to study the effect of pressure, temperature and humidity, that is moistness of air, on the velocity of sound in air. So let us see one by one these factors which will affect the velocity of sound in air. The first point is effect of pressure on velocity of sound in air. Effect of pressure on velocity of sound in air. So in order to explain this effect, let us consider the Laplace's corrected formula for velocity of sound in air, and therefore according to Laplace's formula for velocity of sound in air, Laplace's corrected formula is given as velocity of sound phi is equal to square root of gamma p upon rho, square root of gamma p upon rho, where gamma is the ratio of two specific heat capacity of the gas, that is Cp by Cv, p is the pressure and rho is density of air. And therefore if m represents the mass of air, if m is mass of the air and phi is volume of the air, then density of the air will be equal to mass per unit volume, that is m by phi. And therefore if we put rho is equal to m by phi in the formula of velocity, then we will get phi is equal to square root of gamma p upon m upon phi. Phi is equal to square root of gamma p upon m upon phi, which will be equal to gamma p phi upon m. This volume phi will be shifted to numerator, and therefore phi will be equal to square root of gamma p phi upon m. But according to Boyle's law, we have pressure is inversely proportional to volume, and at constant temperature PV will be equal to constant, and therefore we can say that but at constant temperature PV equal to constant, and therefore as PV is constant, therefore velocity of sound in air will be constant. Phi is equal to constant since gamma and m are also constant. So gamma and m are also constant, and therefore we can say that gamma pv upon m, this total factor will be constant, and therefore velocity of sound in air phi will be equal to constant. That we can say that there will be no effect of pressure on velocity of sound in air. That means whatever may be the change in pressure of the air, there will be no change in the velocity of sound in air, and therefore velocity of sound in air is independent of change in pressure. Now let us consider the ideal gas equation, that is for gaseous medium we have PV is equal to nRT, that is the ideal gas equation. From this equation we can write velocity of sound in air phi is equal to square root of gamma nRT upon m, or for n is equal to 1, that is for 1 mole of gas, phi is equal to square root of gamma RT upon m, square root of gamma RT upon m. So this will be the effect of pressure on the velocity of sound in air. Now let us consider the second factor, that is effect of temperature on velocity of sound in air. So on velocity of sound in air, what will be the effect of temperature, that we will have to study. So for that purpose, let phi0 represents velocity of sound at temperature T0. Let phi0 be the velocity of sound at temperature T0 and phi be the velocity of sound at temperature T. So if phi0 and phi are the velocities of sound at temperatures T0 and T respectively, then we can write phi is equal to square root of gamma RT by M as, so this formula will become now as phi0 equal to square root of RT0 upon M, phi0 equal to square root of RT0 upon M, and phi is equal to square root of R gamma RT upon M, gamma RT upon M, where M is the molecular weight. M is the molecular weight. Then taking ratio of phi and phi0, we can write phi by phi0 equal to square root of gamma RT upon M divided by square root of gamma RT0 upon M. In the form of product, it will be written as square root of gamma RT upon M into M upon gamma RT0. From this mm and gamma r will get cancelled and we will get square root of T by T0. So from this formula it is clear that phi by phi0 is equal to square root of T by T0. Therefore we can say that the velocity of sound in air is directly proportional to square root of temperature. Velocity of sound in air is directly proportional to square root of temperature. That means if there is increase in temperature, velocity of sound will increase. If there is decrease in temperature of the air, then there will be decrease in the velocity of sound in air. And therefore now, suppose 0 degree Celsius temperature is taken as T0, that is if T0 equal to 273 Kelvin. So in terms of degree Celsius, that temperature will be equal to 0 and therefore in terms of Kelvin it will be 273 Kelvin, and the higher temperature T will be equal to T plus 273 Kelvin, T plus 273 Kelvin, and therefore from this we can write the ratio of phi by phi0 as it is square root of T by T0. It will be written as square root of T plus 273 upon 273, because T0 is taken 273, T will be equal to T plus 273, that will be written as T upon 273 plus 1. So separating denominator it will be written as T upon 273 plus 273 upon 273, and which will be equal to T upon 273 plus 1 under root. That will be equal to square root of, rearranging the terms we can write square root of 1 plus T upon 273, square root of 1 plus T upon 273, and therefore we can write phi by phi0 equal to square root of 1 plus alpha T, square root of 1 plus alpha T, where alpha is taken as 1 upon 273, 1 upon 273 equal to alpha, and therefore phi by phi0 equal to 1 plus alpha T under root, and therefore it will be written as, then we can write it as phi is equal to phi0 into 1 plus alpha T raised to half, phi0 into 1 plus alpha T raised to half, because it is under root. 1 plus alpha T is in root, therefore its index is taken as half. Then as alpha is very small, by using binomial expansion we can write phi is equal to phi0 into 1 plus half alpha T, phi is equal to phi0 into 1 plus half alpha T, and the next higher power terms of alpha will be neglected. and therefore only we will get phi is equal to V0 into 1 plus half alpha t. That will be written as phi 0 into 1 plus half alpha is 1 upon 273 into t. So 1 plus half into 1 upon 273 into t, that comes out to be phi 0 into 1 plus t upon 546. Phi 0 into 1 plus t upon 546, and therefore we can write phi is equal to phi 0 plus phi 0 upon 546t. Phi 0 upon 546t. Now putting the value of velocity of sound in air at 0 degrees Celsius temperature, that is phi 0 equal to 332 meter per second. So in this point only, in this place we have to write phi 0 equal to 332 meter per second, and therefore we will get phi is equal to phi 0 into 273 upon 546t. Phi 0 plus 273 upon 546t, which comes out to be phi 0 plus 0.61t, and therefore from this relation it is clear that if there is increase in temperature by 1 degree Celsius, then velocity will increase by the factor 0.61, and therefore from this equation it is clear that there is linear variation in velocity with change in temperature. And therefore now let us see the third point which will affect the velocity of sound in air, that is effect of humidity, that is moisture present in the air, on velocity of sound in air. So what will be the effect of humidity or moistness present in the air? Now the humidity or moistness of air depends upon amount of water vapor present in it. If amount of water vapor present in that air increases, then we can say that the humidity of that air is large. And therefore in order to study this effect of humidity, that is effect of water vapor present in air, let us consider some of the terms, such as let rho m represents density of moist air. Rho m is density of moist air, and rho d is the density of dry air. Rho d is the density of dry air. Similarly, let phi m represents velocity of sound in moist air. Velocity of sound in moist air is phi m, and phi d represents velocity of sound in dry air. Phi d represents velocity of sound in dry air. Then phi is equal to square root of gamma p by rho. That equation becomes, this equation will now become as phi m equal to square root of gamma p upon rho m. Phi m is equal to square root of gamma p upon rho m, and phi d is equal to square root of gamma p upon rho d. Phi d is equal to square root of gamma p upon rho d. Therefore taking ratio phi m by phi d, we will get phi m by phi d equal to square root of gamma p upon rho m divided by square root of gamma p upon rho d. Again in the form of product we can write it as under root gamma p upon rho m into rho d upon gamma p. Gamma p will get cancelled, and only under root rho d upon rho m will be left, and therefore from this we can say that phi m by phi d is equal to square root of rho d by rho m. But if you compare the density of dry air and moist air, we have, but density of dry air is greater than the density of moist air. Density of the dry air is greater than the density of moist air. That is, rho d is greater than rho m. density of dry air is greater than density of moist air, that is rho d is greater than rho m, and therefore from above equation we can say that phi m must be greater than phi d. Phi m must be greater than phi d, as phi m by phi d is equal to rho d by rho m, rho d by rho m, and therefore as velocity and density are inverse proportion, therefore as density of dry air is greater than density of moist air, therefore velocity in moist air must be greater than velocity in dry air, that is phi m is greater than phi d, and therefore we can say that the velocity of sound in moist air is greater than velocity of sound in dry air. That means as the humidity or moistness of the air increases, the velocity of sound in that air increases. So this will be the effect of humidity or moistness. And now let us see next point, that is principle of superposition of waves. Principle of superposition of waves, that is mixing of waves. Now this principle will be stated as when two or more than two waves traveling through the medium arrive at a point of the medium simultaneously, each wave produces its own displacement at that point independent of the other, and the resultant displacement at that point is equal to factor sum of the displacements due to these waves. The statement of this principle of superposition of the waves is given as when two or more than two waves travel through the medium and arrive at a point of the medium simultaneously, then each wave produces its own displacement at that point independent of the other, and the factor sum of the displacements due to these waves is equal to factor sum of the displacements due to all these waves, that is resultant displacement at that point will be equal to the factor sum of the displacements due to all waves. So for two waves we can say that when two waves traveling through the medium arrive at a point of the medium simultaneously, each wave produces its own displacement at that point independent of the other, then the resultant displacement of these two waves will be equal to factor sum of the displacements due to these waves. Here factor sum means if these waves are meeting in phase, there will be addition of their displacements, and if the two waves are meeting opposite in phase, then there will be decrease in their displacement.